Hello, everyone. Thank you so much for coming to my session. I am really excited to be here at Velocity. I am Alena Hall. I work on Azure at Microsoft, and I do these things. And I'm going to talk to you about building systems for distributed data processing and streaming data with Apache Kafka and Spark. So data. Data is produced every second. It comes from millions of sources, and it is constantly growing. But have you ever thought of how much data you actually personally are generating every day? There is data that is generated as a direct result of our actions and activities. For example, if you're browsing Twitter, using mobile apps, performing some financial transactions, using a navigator in your car, or booking a train ticket, or creating a document online, or starting a YouTube live stream. But that's obviously not it. For example, performing a purchase where it seems like we're just buying one thing, it might generate hundreds of requests that would send and generate even more data. Or saving a document in the cloud doesn't mean storing it on one server, because we need to replicate it across multiple regions for fault tolerance and availability. Performing financial transaction doesn't just mean performing one domain-specific operation. It also means storing logs and detailed information about every single micro step of the process to be able to recover things if they go wrong. It also means analyzing some peripheral information about it to determine if the transaction was fraudulent or not. So we log tons of data, we cache things for faster access, we replicate data and set up backups, we save data for future analysis. But also there is data that we track that is being constantly produced by systems, sensors, and IoT devices. So it can be regular system metrics that capture state of web servers, their load performance, or data that is being sent from instrumented web applications. Or it can be heart rate data, or blood sugar level data, or airplane location and speed data to build trajectories to avoid collisions. It can be real-time camera monitors that observe spaces and objects to determine anomalies in process behavior. If we think about it, some of the data is collected to be stored and analyzed later, but some of the data is extremely time-sensitive. Analyzing logs of a regular website is not super urgent if we're not risking anyone's life here. Keeping track of credit card transactions is a little bit more time-sensitive because we need to take action immediately to be able to prevent the transaction if it's fraudulent. But there is something even more critical, like monitoring health data of patients, where every millisecond matters. And all of these real-life criteria of where and how the data is generated, what is the frequency of changes and updates in the data, how fast we need to react to those changes, it all translates to technical requirements for building a data processing pipeline and systems. So we need to be able to build solutions that are able to receive data from a variety of sources, that are able to perform specific computation and analysis of the data on the fly, and possibly perform an action as a result. And we can divide how we think about such architectures into two conventional parts. For example, data ingestion and decoupling layer as a decoupling layer between sources of data and destinations of data, and processing and reacting. So let's look at some of the challenges with the first part. When we, as engineers, start thinking of building distributed systems that involve lots of data coming in and out, we have to think about flexibility and architecture of how these streams of data are being produced and consumed. On earlier stages, we might have just a few components, like a web application that produces data about user actions. Then we might have a database that is supposed to store all this data. And at this point, we usually have a one-to-one mapping between data producer, which is our web application, and data consumer, which is a database in this case. But when our application grows, infrastructure grows, and we start introducing new software components, for example, a cache or an analytics systems for improving user flow, which also requires our web application to send data to all those new systems. And if we introduce a mobile app in addition, that is an entire new source of data that we have to interact with. And eventually we grow, and we end up with many independent data producers, many independent data consumers, and a lot of different sorts of data flowing between them. And there are challenges. How do we make sure that our architecture doesn't become too cumbersome with so many producers and consumers, especially when the same data should be available for some consumers after being read by other consumers? How do we prepare for the need to scale based on changes in rates of events coming in? And how to ensure that data is durable and we won't ever lose any important messages? So let's talk about Apache Kafka. Apache Kafka is an open source streaming system. Kafka is used for building real-time streaming data pipelines that reliably get data between many independent systems and applications. It allows publishing and subscribing to streams of records and storing streams of records in a fault-tolerant and durable way. It also provides a unified, high-throughput, low-latency, and horizontally scalable platform that is used in production in thousands of companies. So to understand how Kafka does those things, let's look at a few concepts. So Kafka is run as a cluster or on one or more servers that can span multiple data centers. Those servers are usually called brokers. Kafka uses Zookeeper to store metadata about brokers, topics, and partitions. Topic is a core abstraction that Kafka provides for a stream of records. And you can think of a topic as a distributed, immutable, append-only, and partitioned commit log, where producers can write data and consumers can read data from. And each record in a topic consists of a key, a value, and a timestamp. A topic can have 0, 1, or many consumers that subscribe to the data written to it. And Kafka clusters durably persist all published records using a configurable retention period, no matter if those records have been consumed already or not. Topics are also partitioned. Each partition in a topic is an ordered, immutable sequence of records that is being continually appended to a structured commit log. All records in the partition have an offset, which is a number that uniquely identifies each record within the partition. And each individual partition must fit on a broker that hosts it, but a topic can have many partitions distributed over many servers so that it can handle arbitrary amounts of data. Each partition can also be replicated across configurable number of brokers for fault tolerance. And each of them can act as a leader that handles all of the read and write requests, or as a follower that replicates the data from the leader. And some brokers can act as leaders for some partitions and followers for others. So it guarantees the load that is well balanced within the cluster. So let's explore how we can actually create a Kafka topic. And for this example, I'm using Kafka on Azure, but it should be similar whenever you might want to run it. So I'm located in my Kafka cluster, and I'm using create command for the topic named new topic. And to check that it exists, I'm using the list command here. And when it's done, we see that here is a new topic. So after we have topics, there are producers that can publish data to topics of their choice, and consumers that can subscribe to topics and receive messages. Consumers can be independent consumers, or they can act as a part of a consumer group. So Kafka not only helps with ingesting big amounts of data, but also works really well for small data in environments with numerous systems that exchange data in a many-to-many fashion. It allows flexibility in pace for consumers and producers, and it scales really well, and it is really fast. Now, sometimes we need a system that is able to process streams of events as soon as they arrive on the fly, and then perform some action based on the results of the processing. It can be an alert or notification, or something that has to happen in real time or near real time. And even though we're talking about Apache Spark today also, it doesn't mean it is the best choice for any system that wants to build a stream processing platform. Choice for a stream processing system fully depends on criteria like latency, community adoption, integration with existing frameworks and tools that you're going to be using. So let's look at some leader-of-the-market stream processing systems. I think the oldest one is Storm, where it is a true stream processing platform. That means the messages are processed as soon as they arrive, without waiting for other messages in the batch. Storm is pretty good. It does not support some of the operations for processing like Spark does. Kafka has streams, a functionality where it is very well integrated with Kafka for data ingestion, and it's pretty lightweight. So if you have data ingest happening through Kafka and Kafka only, then that might be a good option to look at. And Flink is pretty new streaming platform that is by far, I think, the most advanced and innovative. It has a very passionate community. It has a little bit smaller community and smaller company adoption because it's pretty young. And Spark is the most, I think, popular and generally used streaming platform that is most well known for its micro-batch stream processing method. So let's talk about Spark in this talk. Spark is an open source project for large-scale distributed computations, and you can use it to build real-time streaming applications that transform or react to streams of data. It is kind of similar to MapReduce, but more powerful and much faster. It supports more types of operations than just map and reduce. It uses directed acyclic graph execution model and primarily operates in memory. And as of the latest Spark release, it supports both micro-batch and continuous processing execution modes, which we'll talk about a little later. And it can be used with a variety of schedulers, including Hadoop Yarn, Apache Mesos, Kubernetes, and it can also run in a standalone mode. What you can do with Spark is batch processing, stream processing with structured streaming and just regular streaming, machine learning, graph computations, many interesting things. If you have never seen what Spark code looks like, this is a simple Spark program written in Scala. It takes data, text files from remote location, performs a series of operations. Here it's calculating word count and saving data to remote location as a result, just for reference. Now, how does Spark really work? We submit jobs to run on Spark. And on a high level, when we submit a job, Spark creates an operator graph from the code and submits it to the scheduler. And their operators are divided into stages of tasks that correspond to some partition of input data. And Spark has physical nodes called workers that is where all the work happens. There is a driver process that coordinates workers and overall execution of tasks. Executor is a distributed agent that is responsible for executing tasks that run on worker nodes. And task is just the smallest individual unit of execution. So Kafka is really great for durable and scalable ingestion of streams, coming from many producers to many consumers. Spark is great for processing large amounts of data, including real-time streams of events. Now, how do we combine Apache Kafka and Spark together to achieve our goals? We will look at an example on how to do this. And for this example, I am using Kafka and Spark on Azure using services like Databricks and HD Insight. This means I don't have to manage infrastructure because Azure does it for me. But you will be able to follow along no matter what you use for Kafka and Spark. There are detailed instructions of how to create clusters, and I will provide links at the end of the talk. So before we go to an example, this is what I have provisioned. I have a Kafka cluster, a Spark cluster in the cloud. I have peered the virtual networks of Kafka and Spark so that the nodes can see each other and talk to each other. And I'm going to be using public sources of data like Twitter and Slag. So I have created API keys and configuration keys to work with those sources. And I'm also going to be showing examples in interactive environment of Azure Databricks notebooks, which is really cool for demonstrations. And let's see what it looks like. This is a Databricks portal. And here I have a cluster with 4 nodes, and I have a few notebooks attached to it. So if we click on one of them, we can see that there are code cells. And for the presentation, I can run it using Shift-Enter, and it will execute the logic. So let's look at a real practical example. And we're not going to look at health data tracking or airplane collision example or any life or death kind of example, because I know that there are people who might want to use it in production for real-life scenarios. So we're going to look at a very atomic and specific example that would be a great starting point for many other use cases. And the main points that it will demonstrate are how to build a decoupling event ingestion layer that would work with multiple independent sources and receiving systems, how to do processing on streams of events coming from multiple input systems, how to react on outcomes of processing logic, and how to do it in a scalable, durable, and simple fashion. So imagine that you're in charge of a company and you have quite a few competitors in your industry, and you want to make sure that your products and tools are top quality. And here as an example, I'm using Azure because there are a lot of tweets about Azure, and I'm interested in what people think about it, and what goes well, and what things could be fixed. So as an example, we're going to be looking at statements about Azure everywhere on the internet. It can be Twitter, Facebook, GitHub, Stack Overflow, anywhere. Hundreds of potential sources. There are many things that we can do with statements about Azure for analysis. Some of it might require reaction and be time sensitive, but some of it might not be time sensitive. And because I really want the example to be concise, atomic, and general, we're going to use feedback about Azure coming from public data sources like Twitter and another data source like Slag, where people can share their thoughts about Azure, let's say, internally. And as a result, we'll be watching and analyzing incoming feedback on the fly. And if it's too negative, we will need to notify certain groups and be able to fix things as soon as possible. And if it's positive, then we will track it as well, but we don't really need to give an immediate response. So our input feedback data sources are independent, and even though in this example we're using just 2 data sources, there could be literally hundreds of them, and they could be used for many processing tasks at the same time. So in these situations, what we can do is we can build a streaming system that will use Kafka as a scalable, durable, fast decoupling layer that performs data ingestion from Twitter and Slack and potentially more sources. And we can use Spark for analysis of events, determining sentiment in near real time. That would raise notifications in case of positive and negative outcomes of processing. So first part for us is analyzing feedback from Slag. For that, we need to basically have messages sent to Slack. And here I'm generating them and doing it programmatically. So let's figure out how to send messages to Slack. Here is the Slack message generator notebook. And I'm using Slack API, so I need Slack API token. And I need some Slack functions for working with session and sending messages to channels. So I have two channels, feedback and hi. And let's try sending a simple message to Slack to check whether that works. So running that cell, here is a message. So that works. OK. Now, after we can send messages to Slack, we need to listen to new messages. And we need to make sure that we're listening under specific channels focused on a specific topic. For us, it's Azure. And as soon as we find them, new messages, we will send them to a specific Kafka topic. So let's see how the listener is implemented. So this is my second notebook for a listener. And I also need the Slack session and API token. Here I'm using the feedback channel in Slack. And I need a Kafka Producer to send messages to Kafka if there are new ones in Slack. And then I need to implement Slack message posted listener class with onEvent method that I redefine and basically filter out messages from the right channel that contain certain topics and sending them to Kafka. And after the definition is ready, we need to register the listener. So here is the registration function. And let's run this code. And after that, we need to actually invoke the registration here. OK, so that's done. Now, after we have a listener registered, we need to see if we're actually receiving events. And for that, we need to implement a Spark consumer from particular Kafka topics. So we need to get the Spark consumer working with the Kafka topics, and we need to make sure that we're seeing only events that we are interested in. So let's see how that works. Here is a Spark read stream from Kafka. Format here is Kafka, but if you're using other ingest system like Kinesis or Event Hubs, you can change the format. We're subscribing to the topic we're interested in Kafka, and we are starting from latest offsets because we are interested in the most up-to-date data. And we don't need all the fields here. We need only the value for now, where the actual statement content is. Let's start the output sync to the console to see what data is coming in. So it started. Right now, there are no messages, but we can always send message to Slack, and the listener should pick it up, send it to Kafka topic. So Azure Databricks is cool. This message should appear because it has word Azure in it. There it is. Now it sends something that doesn't have word Azure in it, like velocity is cool. OK, we should not find this message. OK, so that seems to work. Now, to make sure it's not a coincidence, let's send something else. OK, we should see that message. Let's scroll down. Scrolling. OK, so here it is. So that works. Now, we have it working with Slack. Now, we need to add another data source like Twitter because the majority of feedback is going to come from platforms like Twitter. So we need to get the latest tweets about Azure and send them to Kafka and make sure that we can receive them to analyze together with other feedback. So we need to have a Kafka producer that would get the latest tweets. So here I am initializing the producer. I need Twitter configuration keys. so that I can access Twitter data programmatically. And here I'm just building the configuration and Twitter factory, and then just starting to send the data to the topic. OK, so here we're sending some events. And let's see if we're receiving them from Spark. Just starting our consumer. OK, here's some data coming out. Jetty support on VS Code. So those are the tweets. Azure C# corner, Azure Stack expense. Yeah, so we see that the data is coming, and that works. Yeah, there is a lot of data. I am actually limited the number of records that come from Twitter because of the Twitter rate limits. So after we have the data, we need to analyze the feedback in real time. Right now, we're currently receiving events from many sources. We need to do sentiment analysis on incoming Kafka events. And the processing logic would be, in case the feedback is very negative, we need to send it to a negative feedback channel for review. And if it's too positive, we also would like to track it and send it to positive feedback channel. So let's see how this works. Here is a consumer. And I'm using cognitive services for sentiment analysis, constructing a few classes to work with the cognitive services, and defining some functions to establish connection for processing requests. And there are two main functions here, getLanguage and getSentiment. That getSentiment returns the value between 0 and 1. 0 is the least positive, and 1 is the most positive sentiment. And the UDF here just returns the value for each stream record. And then I would like to react on this data in real time. So I also need to have a way to send message in the right channel in Slack. So I am defining a toSlack UDF here that has logic to basically branch on the sentiment value. If it's less than 0.3, we're sending it to negative feedback. If it's more than 0.9, just to positive. And we're not logging some of the events. OK, so we should have two columns, sentiment and status, when we launch the stream. Now let's see how that works. I don't think we have any data coming right now because I think I stopped the generator. Now let's generate some messages in Slack, as if it's the internal and partner feedback about Azure. So here are messages coming from feedback channel. OK, positive feedback, got a message. Azure CLI is the best. OK, that's pretty positive. So that works well. Now we should receive something negative. Here is a negative message. Somebody can find some DLL. OK, so this would be something we would need to reply to and track. Now let's add Twitter. Twitter producer. So starting the generation of tweets. And we should be receiving them in this Slack, in this Spark consumer as well. Here you see the sentiment is very positive, and the status is logged in a positive channel. Here is a negative message, and it's all being done on the fly. And then most of the messages are not logged because we don't need to log something in the middle. So let's see what else we can do. Let's actually look in Slack to see, to basically see what state our negative and positive channels are in. Yeah, that all seems pretty negative. This is all positive. OK, so that works. Now, let's just probably stop all of the streams. so that we can go to the next steps. Stop. OK. So what we achieved here is a streaming system where we watch user feedback from numerous independent sources that produce data at their own pace. And we get real-time insights about when we need to take action and pay attention to things that need fixed, where we can plug in many additional independent processing scenarios. Because once we send data to Kafka, it's being retained and available for consumption many times. We cannot worry about strikes in user activity and handling load, because Kafka and Spark allow us to scale out and handle the pressure easily because of partitioning. So now let's talk about some of the interesting things that came out recently. Who have heard about continuous processing mode in Spark? OK, just a few people. So in Apache Spark 2.3, continuous processing mode is an experimental feature that allows very low millisecond latency of event processing. If you remember, Spark traditionally operates using micro-batch pattern, but this is a new feature. So to use it, you can add a trigger to your query, basically saying trigger point continuous, and in the parentheses, you can indicate the checkpointing interval. But so there are a few challenges with this right now because it's very new. It works only with map-like and select-like operations, like flat map, map partitions, filter. Aggregations are not supported yet. Operations like current timestamp and current date are not supported yet. Currently, it is best to use with Kafka as a source and sink for best latencies. And there are no retries on failed tasks. And also, because the architecture of continuous processing is quite different, it has many long-running tasks. And you have to plan your cluster power to be able to handle continuous processing. For example, if you use 20 Kafka partitions, you need to have at least 20 cores in your cluster to be able to handle that. So traditionally, macro-batch, in macro-batch, Spark engine periodically checks the streaming source and runs a batch query on new data that has arrived since the last batch has ended. And this results in latencies around hundreds of milliseconds at best. We have checkpointing intervals, and the offsets for the next batch are recorded before the batch started processing. That means if the record has arrived, it sometimes has to wait till the end of the current micro batch to be processed, and it takes some time. In continuous processing mode that has launched recently, Spark launches a series of long-running tasks that continuously read, process, and write data. And basically, tasks process the events as soon as they are available at the source. And the offsets and the processed offsets are saved to the write-ahead log after every epoch. So because the events are processed and written to the sink as soon as they're available at the source, the end-to-end latency is very low, just maybe a few milliseconds or a sub-millisecond latency. And the interesting thing here is that checkpointing here is completely asynchronous. So that means the tasks continue to run without being interrupted. And it uses Chanty-Lamport algorithm for that. Another thing that might be interesting to some of you is this thing that came out at Build recently, the Kafka API for Event Hubs. So if you're using a cloud provider like Azure, Event Hubs is a streaming service on Azure, conceptually similar to Kafka, but still different. And Event Hubs for Kafka provides an endpoint that can be used by your existing Kafka-based applications as an alternative backend for running your own Kafka cluster. So, and it supports the Kafka Protocol 1.0 and newer client versions. So it will work with existing Kafka applications, including Mirror Maker. All you have to do is just change the connection string. So yeah, if you're interested in that, that might be an interesting thought. Another thing that is kind of cool is the development of operators in big data community to run things on Kubernetes. So if you are interested in running your big data systems on Kubernetes and you're familiar with things like stateful sets, and you know that there are certain questions that might not be addressed by stateful sets, there is a way to address those questions using operator concept. And there has been a lot of new operators coming out for Spark, for other things, and I know that Confluent is going to release their operator for Kafka really soon, and I'm really looking forward to try it. So that is basically Kubernetes' native way to run your distributed systems, especially it helps running stateful systems on Kubernetes. And I'm giving a talk at DockerCon tomorrow about challenges of running big data systems on Kubernetes right now. Those are a few links that might be useful getting started with the example. So if you would like to take a picture of it, this is the right time to do that. Yeah, I'll wait till everybody captures it. OK. Awesome. And thank you very much for listening to my talk. Once again, I'm Alena Hall, Alena Droid on Twitter and GitHub, work at Microsoft on Azure, live in Seattle, like functional programming, and I'm on the board of Shire Software Foundation Board of Trustees. I also organize a machine learning conference called ML for All. It has been in Portland recently. And I am a program committee member for Lambda World Conference, so if you like functional programming, come to Seattle in September. And I have a YouTube channel where I post technical videos sometimes. So thank you very much.